On our coverage of differentiation, and one of the results we will talk about is the mean value theorem. Alright, so to begin with, we first start with the theorem that is stated here, which is that if the function f is well defined on some open interval containing f x naught, it attains either a maximum or a minimum at x naught, and further the function is differentiable at x naught. Okay, so if you're differentiable at x naught, you attain a maximum or a minimum at x naught, and if you are well defined in some open interval around x naught, then the derivative of the function at x naught must be equal to 0. Okay, so this result is really what underlies the operation that we have been learning since high school of setting the derivative to 0 to compute maxima or minima of functions, right? At a maximum or a minimum, subject to differentiability, and of course the function has to be where, the differentiability at x naught implicitly already assumes that the function is defined on some open interval around x naught, right? So subject to differentiability, essentially the derivative at a point of maximum or minimum must be 0. Right? That is what the statement says. Okay, so the proof, let's suppose that x naught is a minimum. Okay, the argument for maximum wouldn't be too different. So the idea is, of course, let's draw a picture. So this is what, for example, x naught would look like, and this is the function, right? So what we're going to do is, given that the derivative exists, we know that the limit of f of x minus f of x naught upon x minus x naught as x tends to x naught must exist, right? And we just have to argue that that limit is necessarily 0, and the way we do that is by first constructing a sequence which converges to x naught from the left, so an increasing sequence which converges to x naught from the left. That will give us one sign of the derivative, and then we will then construct a sequence which actually is approaching x naught from the right, so a decreasing sequence, and that sequence will actually imply the opposite sign on the derivative at x naught. Putting these together, you must argue, it follows that if the derivative is both non-negative and non-positive, it must necessarily be 0, right? So that's going to be the idea. So so the first step in this is going to be that pick a sequence xn such that xn is increasing with respect to n, and xn converges to x naught. In other words, you are approaching from the left, right? In addition, of course, you are assuming that xn is never equal to x naught. Remember, because when we look at the limit of a function as you approach x naught, never is the function value at x naught itself considered, right? So xn does not actually take the value x naught. Now in this case, if you look at f of xn minus f of x naught upon xn minus x naught, okay, and you're looking at the limit of this. So yeah, let's not worry about the limit yet. The point is simply that we know something about the sign of this object. The numerator is guaranteed to be non-negative, right? Because x naught is a minimum, so f of xn is going to be greater than equal to f of x naught. However, the denominator is negative because xn must always be less than x naught, right? Because you are approaching x naught from the left. That implies that this must be less than 0, which implies that the limit of this right, because of differentiability, this limit is exactly f prime x naught, right? Since it is the limit of a negative sequence, the value of the limit must be less than equal to 0. Okay, next, similarly, I'm going to now pick a sequence xn which is decreasing. So next, choose decreasing sequence xn such that again xn is not equal to x naught for all n, and xn converges to x naught, right? Along this sequence you can see that f of xn minus f of x naught upon xn minus x naught is actually going to be greater than 0. Why? Because the denominator is positive, because xn is approaching x naught from the right, and the numerator is positive because x naught is a minimum, right? So once again, the limit of this as n goes to infinity must now be greater than or equal to 0, but this limit must also in fact match the derivative at x naught, right? Because the derivative exists. So if the derivative has to be greater than equal to 0 and less than equal to 0, the derivative must be equal to 0. Okay, so this is fairly straightforward. This is how you argue that you know, if so long as the function is differentiable at any point of a maximum or a minimum, the derivative must be 0. Okay, so next we move on to another important result. This is actually called Rolle's theorem. Okay, so let f be continuous on the closed interval AB, differentiable on the open interval AB, and suppose that f satisfies that the function value at A is equal to the function value at B, right? So you're continuous on the closed interval from A to B, differentiable on the open interval, and at the endpoints of the interval the function value matches, right? Then there exists at least one x in the interval AB such that the derivative at x is equal to 0. Okay, so this is again not very difficult to intuitively believe. Again, if you were to draw a picture at point A and at point B, this function value must match, and the point is that no matter what the function does in the interim, so it must actually have at least one point where the derivative is 0, right? And the way I have drawn it, in fact, there seem to be several points where the derivative is 0. Right? All right. Yeah. Okay, so the proof is actually fairly straightforward. First, you have to take care of the trivial case where the function is identically equal to f of a throughout, right? The function basically remains constant over the closed interval ab. That is, f of x is equal to f of a for all x in ab, right? In this case, we know that the function is just flat in the interval a to b, so its derivative must be 0 at all the intermediate points. In this case, f prime x must be 0 for all x in AB, right? So that's the trivial case that's been addressed. The non-trivial case is that this is not in fact the case. That is, f is not identically equal to f of a for all x in a and b in the interval from a to b. Okay, in this case, one can argue that f must attain either a maximum or minimum between a and b. So case 2 is just the opposite of case 1, so I won't write it again. In this case, f attains a maximum or a minimum in the interval from a to b, right? So this is actually fairly straightforward. Because you're not identically equal to f of a throughout, at some point the function must either take a value that is greater than f of a, or it should take a value that is less than f of a. If at some point it takes a value greater than f of a, then there must in fact be a maximum, and that maximum, that maximum should be in the open interval from a to b. If at any point of time the function takes a value less than f of a, there must therefore be a minimum in the open interval ab. In either case, there is either a maximum or minimum, right? Let x naught be that point, and then by the previous theorem we know that the derivative must be 0. Let x naught denote that point, then by previous result right, and that would complete the result. Okay, so far we have seen two things. Firstly, that if a function is differentiable, then the derivative must be 0 at maxima and minima. And now here the second Rolle's theorem tells you that if the function is subject to differentiability, if the function value is equal at 2 points a and b, there must be an intermediate point where the derivative is 0. Okay. Next we will prove the mean value theorem, which is in fact simply a generalization of Rolle's theorem. Okay, so the mean value theorem is stated as follows. Hypothesis is similar. Let f be continuous on the closed interval ab, differentiable on the open, okay, then there exists when I say there exists, it's implicit that there exists at least one, right? X in AB such that the following condition is true. The derivative at x is in fact equal to f of b minus f of a upon b minus a. Alright. So you can see that if f of b is equal to f of a, this of course matches Rolle's theorem. So in that sense, the mean value theorem is a simple generalization of Rolle's theorem, right? And there is a very similar graphic interpretation that you can cook up with respect to the mean value theorem, right? So you have, let's say this is a, this is b. The function does whatever song and dance you like between a and b, right? Now, what is this f of b minus f of a upon b minus a? It is the slope of this line that basically connects f of a and f of b, right? So what we are saying here is that at some point the function in between a and b, at some point the function should have a slope that in fact matches the slope of this line, right? So that, for example, might be this point. Right? So that's your graphical interpretation of the mean value theorem. Okay, so the proof is essentially just two lines because it's going to follow trivially from Rolle's theorem. Okay, so let g of x be defined as follows. G of x is equal to f of a plus f of b minus f of a upon b minus a times x minus a. Okay, so if you think about it, we have basically defined g to be this straight line. Okay, it's, yeah, check that it's of course linear with respect to x. At x is equal to a, g of x is equal to f of a, and at x is equal to b, g will take the value f of b. Okay, so I mean that's an easy thing for you to check. So g is defined as follows over the entire interval, and we note that so G of A must be equal to f of A, G of B must be equal to f of B. Okay, so now what you can do is define the function h of x as f of x minus g of x. Okay, if you do this, then h of x basically takes the value 0 at A and it takes the value 0 at B. The fact that it does that implies that you can apply Rolle's theorem to h to argue that there must exist a point where the derivative of h is 0, right? And a point where the derivative of h is 0 is precisely the point which satisfies the mean value theorem. So to complete the answer, all you need to do is apply Rolle's theorem to h, right? And that would complete the proof. Okay, so it's really, I mean, it's a generalization, but it's also a trivial generalization of Rolle's theorem. All right, which in turn is an easy consequence of the fact that differentiable functions must have a derivative of 0 at maxima and minima. Okay, so those are the main results for this lecture. What we will do next is basically study a few corollaries that follow, in fact, from the mean value theorem. Okay, so for this corollary again, suppose that f is differentiable on the open interval AB. Okay, now there are some 4 assertions that we will write, I guess 3. If f prime x is equal to 0 for all x in a p, then f is constant. Over a comma b. Okay, so if the derivative is identically 0 over some interval, then the function must also be constant over the interval. The converse is trivial. If the function is constant, we know that the derivative is 0. Now we are proving a converse to that, right? Which is that if the derivative is 0 across an interval, then the function must in fact be constant, right? Implicit in this is of course that the function is differentiable. If the derivative of x is positive for all x in this interval, then f is strictly increasing over a comma b. Okay, and then finally we can do a relaxed version of this. If the derivative is non-negative for all x in a p, then f is increasing. More precisely, I can say that f is non-decreasing over the interval AB, right? And all of these are in fact trivial consequences of the mean value theorem. Now, this corollary has been written with respect to the derivative being 0, positive and non-negative. You can write a similar, of course, statement for the derivative being negative and non-positive. Right? If it is negative, then you can argue that the function is going to be strictly decreasing. If it is less than equal to 0, so non-positive, then you can argue that the function would be non-increasing. Okay, so so I hope it's clear why these results all follow quite straightforwardly from the mean value theorem. In particular, the function is defined over this open interval AB, And what you have to argue in each case is, if you pick 2 points, let's say x and y within this interval, suppose the first condition holds that the derivative is 0 identically, then we have to argue that f of x is equal to f of y, right? And why is that? Well, if the derivative is identically 0, apply mean value theorem, and you will see that that f of y minus f of x upon x minus y must be equal to the derivative at some intermediate point, right? So there, so let's call this point, let's say z, right? So this is going to be like a common proof that applies to all of these cases. For x and y in the interval, so for a less than x less than y less than b, well, there exists a z between x and y such that f prime z would be equal to y minus f of x upon y minus x. Okay, so now if the derivative at z is 0, that must imply that f of y is equal to f of x. If the derivative at x is positive, that must imply that f of y is greater than f of x, and so on, right? All of these statements would in fact follow quite straightforwardly in this fashion. Okay, so I will write one more corollary, which is a trivial exercise. If f and g are differentiable on a comma b, and f prime x is equal to g prime x for all x in the interval ab. So you have two functions which are both differentiable on the interval ab such that their derivatives basically match, right? So if their derivatives match, then it must be that f of x is equal to g of x plus c for all x in ab for some c. Okay, so for some constant c, f of x and g of x must basically be offset by the constant c, right? So in other words, if you have two functions whose derivatives match over an interval, then it must be that one function is some constant plus the other function, right? Again, it's easy to see that this is just going to be a trivial consequence of the previous corollary, right? Because what we are saying is that f minus g has a derivative of 0, and if f minus g has a derivative of 0 over the entire open interval, then it must be that this function f minus g is a constant, right? Which is exactly what the corollary states, right? So with that, I will stop here, and we will continue our discussion on the derivative in the next video.